Okay, in the next few slides, I will share with you on how the system properties in terms of pools, still remember pool, don't you, will affect the response of the system. Let's take a look again. Let's refer again to this slide. We have already discussed this slide in week 2. Any dynamic system, we always be able to model it in differential equation, right? Where if you look at this equation, you can consider x as input and y as the output. And because of the dynamic the nature of the dynamic system, the differential equation, the model of the dynamic system will also involve the derivatives of the output and derivatives of the input as well. This differential equation that represent the model of the dynamic system can also be represented in transfer function form. We discussed this also. So what is transfer function? Transfer function is the ratio of output to the input in Laplace domain when we consider all the initial conditions equal to 0. So this is again, I rewrite again the transfer function. Transfer function, if you look at this, the numerator as well as the denominator appear in polynomial function of S. So the numerator has a polynomial order of m, the denominator order is n. That means I always be able to factorize the numerator into m factor of a first order polynomial. While the denominator, I will always be able to factorize it into n number of first order polynomial. And then we discussed also in week 1 that once you factorize the denominator and the numerator, you should be able to analyze the poles and the zeros of the transfer function, right? In this case, of course, minus p1, minus p2 until minus pn, all of them are the poles of the system, and minus z1, minus z2 until minus zm are the zeros of your system. Let's take a look again on the same transfer function. Apparently, the poles from minus p1, minus p2 until minus pn not necessarily to be a real number. Some of them can be a complex number. So let's take case P1 is a real number, P2 is a real number, but probably P3 is a complex number. But if you have pole in complex number, the complex pole will never be alone there. It will always be accompanied by the conjugate of that complex number. So again, if P1 is real, P2 is real, P3 is complex, there will be another pole, probably P4, which is the conjugate of the complex pole P3. So in short then, mathematically, I can rewrite this transfer function into this form, where this part indicates the real poles, and this part, the second part, indicates a pair of complex conjugate poles. Lambda 1 bar is the conjugate of lambda 1 in this case. Let's take this example. So I want to identify the poles of this system. What should I do? I need to factorize the denominator. After I factorize it, the denominator will be equal to this one. S times s plus 4 times s squared plus 4s plus 29. I still have a second order polynomial from this part. If I factorize it further, the polynomial will become like this. So I will have one pole which is equal to 0. My second pole is equal to minus 4, and I have a pair of complex conjugate pair of pole, which is equal to minus 2 plus and minus 5j. So in this case, again, I will have two real poles and a pair of complex conjugate poles. So it agrees with what I said before. A complex pole will never be alone. It will always be accompanied by its conjugate. Talking about analyzing the poles, I want to introduce you with new terminology. We call it as a characteristic equation. What is characteristic equation? Characteristic equation is the denominator of your transfer function equal 0. So ds equals 0, that is the characteristic equation of your transfer function. And mathematically, finding the roots of this characteristic equation, you will find the poles of the system, right? Because if you find the roots of the characteristic equation, that means you need to factorize the denominator ds. And then in that way, you can find the poles of the system. One thing that we have to note here, poles apparently will determine the stability of your system. Let's take a simple case here. Let's consider a system with a transfer function of gs, where gs is equal to a divided by s minus a. A is just a real number, any number. And then from this transfer function, of course, you can identify the pole of the system. The pole in this case will be equal to A. The pole of this GS is equal to A. Now let's take a case when to this system we give a unit step input. So the input that is given to the system is 1 over s in Laplace domain. The input is 1 over s. The transfer function is A divided by s minus A. So of course, the unit step response, the response of your system will be equal to the transfer function times the unit step in Laplace domain. After you do the partial fraction expansion, you can rewrite this equation into this form. And then you just simply have to refer to your Laplace table. You can find the unit step response in time domain, and then it's becoming this one. Now let's try to plot this step response, this unit step response in time domain. Let's take a case when A is positive. When A is positive, any real number, A is positive, any positive real number, if you plot the response Ct in time, the plot will be something like this. Why? Because A is positive. If t is increasing, exponential of positive number, if the t is increasing, will go to infinity. The bigger the t, the bigger the exponential of A times t. So if you plot the response Ct in time, will go to infinity. When t is increasing, exponential of At will also increase exponentially. So the response in time will go to infinity, as illustrated in this figure. Now let's take a second case when A is negative. When A is negative and if t is increasing, exponential of negative number, let's say if we have a negative 10, let's say, times t. If t is increasing, if t is approaching infinite number, your exponential of minus a minus real number times t will tend to go to 0 when t is increasing to infinity. So again then, if a is negative, then when time is increasing, your Ct value will tend to go to negative 1. If I plot Ct in time for negative a, the response will be like this. So what do we see here? What we can conclude in here, if we have positive pole, the response will go to infinity. If we have negative pole, negative A, the response will converge to one single value in steady state condition. This is to say that if you have positive pole, the response will go to infinity. That means you have unstable system. Positive pole will give unstable system because the response will go to infinity. If you have negative pole, A is negative, the response will converge to a single value, then we can say that the system is stable. Talking about stability of a system, then I can classify a system into three things. The first one, when you have a stable system, you will have a stable system if the output of the system converts to one single value. An example of a stable system is when you have a response like this. In time, the response, the output will converge to one single value. You might have also unstable system. A system is called unstable when the output of the system will go to infinity for any particular constant input. So, as an illustration, an unstable system will have this response for a constant input. Besides these two, we also know what we call as marginally stable. What is marginally stable? You will have a marginally stable system if, after you give a constant input, the output is continuously oscillating. Something like this, which means the output is not going to infinity, but nor converts to one single value. It keeps oscillating all the time. So this is what we call as a marginally stable system. As a remark of this part, poles, as I mentioned, can be real, but can also be complex. One thing that you have to underline here, if it is complex, there always be another pole that is the conjugate of that complex pole. So if it is complex, they always appear in pair together with the conjugate. And the stability of the system depends on the location of the poles. If you have positive poles, you have unstable system. If you have negative pole, your system is stable.